Hello, welcome to the presentation of real-time vehicle detection and tracking at Junction using Fisheye camera. We are Team Multilayer Perceptron. I'm Muhammad Asafur Rahman, second year undergrad student at BUIT. I'll be presenting the first part of the presentation. We'll start with the problem overview. In this competition, the problem has been divided into two tasks: vehicle detection, vehicle tracking. While solving these problems, we face the following issues. First, highly distortion ratios. Different scale of same object moving in different parts of the image. Moreover, day-night views variance as night view suffers from low quality related to surrounding lighting conditions. Furthermore, exposure introduced with vehicle lights in the night view. Finally, imbalance between different types of vehicles and imbalance between day and night cases. Now, let's have a look at the dataset distribution. The provided Fisheye dataset has around 32,000 images, where 22,000 images were for day cases and 10,000 images were for night cases. As vehicle detection is a part of the object detection problem, and deep learning is proven to be a very powerful tool to solve object detection problem, we'll be using deep learning models to detect vehicles. Among all the experimented models, single-stage detectors like YOLO-based models and efficient DET are proven to be very accurate with very decent FPS. And from the following models, YOLO-based models are proven to be faster, having almost similar accuracy, which makes them perfectly suitable for this competition. To solve the previously mentioned problems, we propose the following solutions. At first, we separated day images from the night, as night images are very different from day images, having issues like night glare, noise, low brightness, which certainly can hurt the day model. To separate night images from days, we use a deep learning model. Here, the input image will be passed to the day-night differentiator model, which will decide if the image is day or night. Then the image will be passed to the corresponding pipeline where the vehicles will be detected. We also noticed there were some challenging cases where our model has not been able to perform up to the task. For example, very big, small, uncommon vehicles and images with cameras. To force our model to learn those cases, we upsample them 10 times more. Finally, we use multi-stage transfer learning to improve our model's performance. In the first stage, our model was trained on the COCO dataset. As the COCO dataset has 80 classes which include person, motorbike, bicycle, traffic lights which don't exist in the Fisheye dataset, it may confuse our model. In the second stage, we use the BDD100K dataset. As the BDD100K dataset has only one class vehicle, thus it's more relevant to the Fisheye dataset. Furthermore, this dataset has images taken at very low brightness which mimics the fisheye night condition. Now let's have a look at the distribution of the BDD100K dataset. The BDD100K dataset has around 73,000 images, for 42,000 images for day cases and 31,000 images for night cases. After introducing our proposed methods, we were able to see significant amount of improvements for both day and night cases. Now let's have a look at some of our results. For the day cases, we can see after introducing our solution, for both false positive and false negative were removed. Similar improvements can be noticed for the night cases too.
Hi, I'm Najibul Haq Sharkar. I'm a second year undergrad student of BUIT, and I'll be presenting the second part of this presentation. After the first submission results, we saw that our proposed methods performed really well on the day dataset, but comparatively worse on the night dataset. So we tried to further improve our models. Firstly, we added a pseudo-labeled day dataset. This should make the model more robust and help handle unseen day cases. Secondly, we tried multi-stage differentially trained ensemble. In the day pipeline, we used a model trained on the day dataset, model trained on the day plus the pseudo-label dataset, and finally a day plus night trained mixed model. We used NMS to merge the outputs. For the night pipeline, we trained the model on the day dataset and then trained it on the night data. We saw that the day dataset contained relevant challenging cases which weren't present on the night data. That is why this training mechanism should improve the night score. We trained two models in this way, one of 1024 scale, and another is of 768 scale. Finally, we used the mixed model here too. Similarly, NMS is used to merge the outputs. As you can see, incorporating this method results in score improvement. Here too you can see that there are a few false positives and false negatives on the day case without ensemble, which aren't present after our improvements. We see similar results on the night case as well. Now let's dive into our model details. Our data differential model is a very shallow feature extractor model. It contains a couple of convolution blocks activated by Licorelu, dense blocks, and a sigmoid layer. The core model in the day and night pipeline consists of a backbone for feature encoding, a neck for extracting different feature maps, and a head for performing the actual detection. Let's dive into the backbone first. It consists of a focus block, alternating convent bottleneck layers, and an SPP block. Three outputs of different scales are taken from the backbone, which are then passed on to the neck for processing. The neck architecture is based on path aggregation network, which has a top-down path and a bottom-up path. The neck takes three outputs from the backbone and outputs three corresponding scales in the head. This architecture preserves accurate localization information. The head takes three outputs from the neck, passes them to one by one convolution block, and the output is then stacked and post-processed to be in the correct detection form. Now let's look at the building blocks of the model. First comes the focus block. In this block, the input image is sliced horizontally and vertically to make a grid. By taking the alternative slices, four different image blocks are made, which are then concatenated together on the channel level. This essentially focuses the image information onto the channels before passing on to a convolution block. The convolution block consists of a convoluted block, a Bayesian layer, and is activated by a hard switch function. The SPP block passes the input to a convolution block, applies max pool of different kernel sizes, and concatenates the output before passing on to another convolution block. This helps making a scale invariant model. The basic bottleneck block consists of a 1 by 1 convolution followed by 3 by 3 convolution. This has a parameter called shortcut, which enables us to use the residual connection. The bottleneck CSP layer passes the input to two different paths. The first uses the aforementioned bottleneck block. The second is just a simple conv block. It then merges the output of these two paths before passing it to another convolution block. The purpose of using bottleneck layers is to condense the features in a specific number of channels. The CSP structure makes the gradient flow propagate through different network paths by splitting the flow. It decreases computation. We used CIU loss during training. This builds on the concepts of GIU loss, which builds on the concept of the IUU loss. Our experiments showed that using CIU loss made the model perform better. This is the complete overview of our model. In the case of tracking, we use the IU tracker method. First, we select a vehicle from an image and calculate its IUU with all vehicles from the next image. The one with the highest IUU is the same vehicle. This method proved very efficient and effective. So now we'll show you the detection and tracking output of our model for both the day case and the night case. So in conclusion, we provide a robust model architecture which can handle the challenges of fisheye images and provide real-time object detection and tracking. As you can see, even our ensemble model provides usable FPS given the necessary device. This concludes our presentation. We thank the organizers for hosting such a wonderful competition and thank you to the audience for listening. Now, if you have any questions, please feel free to ask.